Hello and welcome to Chapter 3 where we'll be talking about atoms and elements. Atoms specifically, we'll be talking about the parts of atoms and what makes them up and the relative sizes. And we'll be talking about elements, the smallest bits of which are atoms, so that we can then build to a connection of one atom of a kind of element to another atom of a different kind of element, and how that makes something called molecules, which are the basic building block of substances. And substances, of course, are things that have a specific set of chemical and physical properties. So why are we going to look at this sort of idea, this idea of atoms and molecules and elements? Well, what we're trying to understand is how the universe around us that we can see works, and to do that, we need to understand the fundamental building blocks of that universe, which are atoms and molecules made up of connections of atoms that are bound together. So, for instance, the thing that we observe as air is actually made up of nitrogen and oxygen and carbon dioxide molecules, which are made up of nitrogen atoms and oxygen atoms and carbon and oxygen atoms combined together. Salt water, which we see as the ocean, is actually made up of sodium atoms and chlorine atoms, which are actually ions because of something we'll describe later. There's some carbon dioxide dissolved in there. There's some water molecules dissolved in there, which are made up of hydrogen atoms and oxygen atoms. And we can go through all of these different descriptions, including the incredibly complex molecules made up of hundreds and thousands of atoms just in one substance with one set of properties that makes up the sort of things that make up the tissues and organs and chemistry that goes on inside your body. So to understand this microscopic world, we actually have to understand, or to understand the macroscopic world that we see, I should say, we have to understand these microscopic and submicroscopic atomic world that makes it up. So the thing to remember here, if nothing else that you take home from this, I want you to have some idea of how incredibly small atoms are. I mean, they are the smallest identifiable unit of an element, meaning that if I have a sample of carbon, a chunk of carbon, and I look at a tiny bit of it, and I have a smaller chunk of carbon, and I look at a tiny bit of that, and I keep cutting it in half and cutting it in half and cutting it in half, it's still going to act like carbon. It's still going to be carbon. It'll have all the physical and chemical properties of carbon. It's carbon. When I get down to the individual atom of carbon, one atom, okay, then that one atom of carbon can't get split up any more than that and still act like carbon. If I cut this in half as a carbon atom, it's not going to act like carbon. That's not acting like carbon anymore. Alright, so now how incredibly small are atoms? Let's think of it this way. Let's take a handful of carbon. So you get like a little tiny chunk of charcoal or something like that that's almost entirely composed of carbon atoms. It's an elemental form of carbon, just carbon atoms in it. We're going to take that chunk of carbon and we're going to take every single atom in that carbon, or in that coal, and we're going to blow it up to the size of a marble. Okay, so each atom, which is grossly bigger than an actual atom, this dot here, but we're going to take each of those and make them the size of a marble. Marble. Huh? So how much space do you think those marbles would take up? That one little chunk of charcoal, turn each atom into the size of marbles, what does that fill up? Do you think it'll fill up a 5-gallon bucket? Think about it, vote on it, yes or no. More. Okay. How about the whole room that you're in right now? It could be a small room, could be a big room, who knows, but will it fill up that room? More. It's going to fill up even more space. Alright, how about whatever building you're in? Could be your house, could be College of DuPage, whatever. Do you think it'll fill that entire building? Yeah, it'll fill up that whole building and still more. Okay, so where does this get to? Illinois, fill up the whole United States, fill up North America. If you actually do this and you look at how much room this fills up, you take the atoms in that little chunk of charcoal that you had, turn them each to the size of marbles, what we get is the entire surface of the Earth buried in marbles to a depth of 50 miles. Okay, so 50 miles deep, the whole surface of the Earth, with just the number of atoms in a handful of atoms, but now you make them the size of marbles. So that's such a huge increase in size that now you have this many atoms present. Okay, so they're incredibly small to be able to fit that many 50 miles deep of marbles compacted into a smaller size into a tiny little bit of a handful of carbon atoms in charcoal. So let's put a number on that. Let's take a grain of sand, okay, so an individual tiny grain of sand, and look at the atoms that are in that. Well, that tiny grain of sand has somewhere in the neighborhood of 1 times 10 to the 20th individual atoms of material present in that grain of sand. So how much is that, right? Let's write it out. 1 times 10 to the 20th, we know scientific notation, that means there's 20 zeros. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's about 20. So that many. So if you counted them all, you'd have to count to this number, which is ridiculous because you'd never count to that high a number because you'd die of old age before you got anywhere close. But that's how many atoms can fit in one tiny grain of sand material. Okay? So think of nothing else of this chapter. Keep in mind how incredibly crazy small atoms are. Now we're going to talk a little bit about protons. And we've discussed protons already earlier in the semester where we talked about them in Chapter 2 and Chapter 1. We talked about the parts of the atom. So remember we represented protons by a lowercase p and a superscript plus. Now when we talk about an element, we talk in an atom of an element, we have an item we call the atomic number. We refer to that with the variable z. Now what this represents for a particular atom specifically is the number of protons that you would find in the nucleus of that atom. Now each of these protons is positive. That's why we have the little superscript positive sign above the proton. And we give each of those a numerical value of a +1 charge. That's what they're defined as. We're also going to talk about the mass of a proton. And the mass of a proton can be measured in what's referred to as AMUs, or atomic mass units. Okay, so an atomic mass unit is specifically defined as 1/12 of the mass of a very specific carbon atom nucleus. And when you work that out in terms of grams, which remember about 10 grams is the weight of a dime and about 450 grams is about a pound. So this is 0.24 zeros followed by 167. So 1.67 times 10 to the negative 24th grams. That's a really tiny amount. Now, protons are a pretty significant portion of the mass of an atom. And the mass of a proton is defined as about 1.0 AMUs. So let's take a look at this concept problem here and see if we can use our definitions of atoms and that sort of thing to really check to see if we know where we're at here. So we have graphite in a pencil that's made out of carbon, and we have the gemstone diamond that's also made out of carbon. So both of those things are carbon atoms. So they might behave differently because of how they're connected, how those carbon atoms are connected to each other. And they look differently for the same reason. But there is something that's the same, specifically about the nucleus of those carbon atoms. So what do you suppose that commonality really is? Well, it turns out that that commonality is that each of those carbon atoms has exactly 6 protons. So even though the connections might differ, which might give them different chemical and physical properties, in terms of protons, they have exactly the same number of protons, regardless of whether the carbons are part of graphite or the carbons are part of diamond. Now, when we look at these different chemical symbols so that we can talk about individual atoms of certain elements, what we're looking at is basically an abbreviation of the chemical name. We don't want to have to say hydrogen every time we have a molecule or a compound that has hydrogen in it. So for instance, for the element hydrogen, we can use the letter H, uppercase H. Now, capital versus non-capital is pretty critical here because there's only 26 letters in the alphabet and there's over 100 elements. So obviously we can't give all of them a one-letter abbreviation. For a lot of elements, nitrogen, oxygen, carbon, hydrogen, one letter and a letter that corresponds to the English name for the element works really nicely. For other elements, we sometimes see the Greek or Latin name go into the symbol. So ferrum, iron. Atoms of iron are designated with the symbol uppercase F, lowercase e, for ferrum. Sometimes we go by the place where that particular element was discovered. Like in Europe, we have europium, uppercase E, lowercase u. Sometimes if, especially with the elements really far down on the periodic table, we have elements that are named after the person who discovered them. Or we honor another scientist, perhaps, just as a great scientist by naming an element after them. So, for instance, curium, uppercase C, lowercase m, is designated the symbol for that element. So here we have the periodic table. A lot of these things are on here, and we have even more on our periodic tables, and they have periodic tables that have even more on top of that. But here's a couple of things that we can see on this periodic table. One, we can see the name of the elements. That's written right there up the top on this one. We see the number of the element. It increases as we go from left to right, top to bottom. And remember, the number here is the atomic number, Z, which corresponds to the number of protons for that element. As you can see, the element is basically defined by the number of protons in the element. The element that we're looking at has an atom with 5 protons in it. The only thing it could be is the element boron, atoms of the element boron. I said before that carbon had 6 protons. Every single carbon will have 6 protons. On the periodic table, we always also find the chemical symbol, Be for beryllium, Mg for magnesium, for instance. These are the basic things that you'll find on just about every periodic table. Now, the second part that we find in atoms we talked about before are electrons. Now, electrons are the negative part that's in the atom that opposes the charge of the positive protons. And remind you, we use the symbol lowercase e with a superscript minus. Okay? So a neutral atom, one that has no net charge to it, will have the same number of protons as electrons. Okay? So we'll have the same number of each. That way, for every positive charge we have one negative charge on top of that. So electrons, -1 charge. Now, the negativity is what helps the electrons stay attached to that particular element's atom. You have the nucleus in the center, which contains all the protons and the positive charge, and surrounding that, you have electrons. So if you look at neutral atoms, for instance, you look at a helium nucleus. Helium has an atomic number of 2. It's the second element on the periodic table, meaning it has 2 protons. So it's going to have 2 electrons on top of that. Okay. Carbon has a Z of 6. It has 6 protons. It's also going to have 6 electrons. If it is the neutral version of the atom. And again, neutral just means that there's no net charge. And well, what if we don't have a neutral atom? What if we have an atom that has a net positive or a net negative charge? Well, remember in the center we have protons, and we're actually showing the neutrons here as well. Those are the neutral parts of the atom. They're also in the nucleus. We use symbol N with a superscript of 0 that says neutron. They have mass, which is very close to that of the proton, but no charge. Okay? So if we look at a sodium atom now, and we measure it and find out that that sodium atom has one positive net charge to it, what that means is when we take up all the protons and we subtract the number of electrons from that, we get a +1 net charge. So sodium, if we look on the periodic table, it's the 11th element. That cannot change. This does not become positive because we add another proton to it. That isn't how it works. If we add another proton to sodium, it becomes a different element. It has different properties. So 11 protons means we have 11 positive charges. If it's +1 altogether, that must mean that we have 10 negative electrons to make this all work out. Right? We have 11 protons minus 10 electrons. We have a total of +1 net charge. And when we want to indicate that charge, all we do is we write the element symbol, and as a superscript, we write the charge that that particular element has. Now, when an atom has a charge, we refer to it as an ion. When it has a positive charge, we refer to it as a cation. When it has a negative charge, like the fluorine atom that we're about to look at with a -1 net charge, we refer to it as, it's a negative charge, as an anion. Alright, so we look at fluorine. Fluorine has a Z of 9. It's the 9th element on the periodic table, left to right, top to bottom. That means it's going to have 9 positive protons. If the overall charge is -1, then this must mean that there's 1 extra electron compared to the number of protons we have. So we have 9 protons minus 10 electrons, -1 net charge. Just like you'd expect, we actually have an attraction between a sodium ion and a fluorine ion. These things are actually attracted to each other because of the positive and negative aspects of them, but we have plenty of time for that. We'll get to that later. Okay, so how many protons and electrons are in the lithium atom? Lithium. So to puzzle this out, we have to know where lithium is on the periodic table. So we scroll back to our periodic table. We look at lithium over here. See, it has a Z value of 3. So that means it has Z value is 3. That means it must have 3 protons. It cannot have more, it cannot have less, and still be called lithium. Alright, well, if it has a +1 total charge, that means 3 protons minus some number of electrons is going to equal +1. So we puzzle that out. We see that that means there's 2 electrons. Pretty straightforward. Alright, neutrons. It says here that they're very slightly lighter. This is something your book just gets wrong. And I wrote that up there when I was reading through the book, and I looked at that and I went, you know what? That is just not true. Let me make this point slightly heavier than protons, but they carry no electrical charge. You can basically think of this as almost a proton and electron kind of stuck together. Protons have that approximately 1 AMU size for a proton. A neutron is a little bit bigger, but still about 1 AMU. An electron, we didn't mention this before, is about 1/1800th the size of a proton. So they're tiny. Even though they have a full positive, or a full negative, I should say, it's electron, they're negative. Even though they have a full negative charge, same amount of negative as the protons have positive, they're almost 2,000 times smaller than a proton, which is kind of interesting all in itself. But in any case, back to the story about neutrons. Neutrons, very slightly heavier than protons, but they have no net charge. In fact, if you add up the amount of weight of a proton plus an electron, you get something really close to that of a neutron. I've always kind of thought of neutrons as just the proton and the electron bound together in the nucleus. And there's more evidence that that's kind of how we can think about it when we talk about nuclear chemistry, or reactions that occur inside the nucleus of the atom. Now, you can have different numbers of neutrons in the same kind of atom. I can have carbon, and I can have 6 neutrons in it. I can have, this is carbon. So carbon meaning 6 protons, but this particular type of carbon also has 6 neutrons. I can also have a carbon, meaning 6 protons, that has 7 neutrons in it. Now if we counted all these up, we'd find them, but just trust me, they're there. So the number of neutrons can vary. And when we have a different number of neutrons in the same type of element, so a carbon with 6 versus a carbon with 7, we refer to those differences as there being isotopes of that particular element, meaning ones that have different numbers of neutrons. If you think about it, what that's going to do is that's going to make that atom a little heavier. The one with 7 neutrons instead of 6, well, that's 1/12 larger a mass because of that extra neutron. It's not going to give me any more electrons because we're not adding any more positivity to attract electrons. Neutrons are uncharged, but it is going to make it heavier, and that is going to affect the properties slightly, even though it's still going to basically still behave like carbon does. Now, to kind of keep track of this, we define another value. We define this A variable, which is referred to as the mass number of an atom. Now, the mass number is just equal to the number of protons plus the number of neutrons. So it's just the total amount of stuff in the nucleus. Okay? So we have all of these different things, and we can indicate all of the different parameters of a particular element, or an atom of a particular element, including how many protons, neutrons, and electrons that particular atom of that element has, by showing a whole bunch of superscripts and subscripts around the chemical symbol of the atom. So let's look at a hydrogen, an atom of the element hydrogen. Let's look at one that has 1 proton, because that's our only choice, right? Because it's hydrogen. We look in the periodic table, its atomic number is 1. Let's say that this particular one has 1 neutron and 1 electron. Okay, so 1 of each. Z is the atomic number. That's the number of protons, so that's 1. We'll actually put that at the bottom left-hand corner of the symbol that represents that element. So the symbol for hydrogen is H. That's what this X represents in the nomenclature. Z is the atomic number, so we'll put that in the bottom left-hand corner. So we describe over here as the place for it. A is the mass number, protons plus neutrons, so 1 plus 1 in this case, or 2. That goes in the upper left-hand corner, so it's a superscript, so 2 there. And then C is the net charge, right? That's number of protons minus number of electrons. Now, this is 0 in this case. Typically, you don't see a 0 in the upper right-hand corner. If it's 0, we're just going to say, yeah, that's the default case. We don't need to specify that. So we won't put anything up there in that if that's the case. Alright, so let's look at this again. Let's look at a second example, because these examples are good. We're going to need to be able to do this sort of thing. Let's look at a, I don't know, let's call it carbon, and we'll say it has to have 6 protons because it's carbon and all of them have 6 protons. We'll say it has 7 neutrons. Good. And we'll say it is, it only has 2 electrons. So we're switching it up a little bit here, right? So the atomic symbol for that element, carbon, is C, right? That's the X that goes in the center. Z is the atomic number, bottom left-hand corner. A, which is going to go right here in the upper left-hand corner, is 6 plus 7. Right? Number of protons plus neutrons, that's 13. And the number of electrons is 2, so we figure out the charge as the number of protons minus number of electrons. So that means we have 6 minus 2 plus 4. So we put a plus 4. And that's how we'd specify a carbon atom with 6 protons, 7 neutrons, giving it a 13 total in the nucleus, and 2 electrons, meaning that the 6 protons minus 2 electrons gives it a charge of positive 4. One last example of this, because I'm driving nuts with it otherwise. Let's erase the ink again. What if I just tell you we have, let's see, sodium plus. And I tell you that the sodium plus has an atomic, has a mass number, not an atomic mass number, but a mass number, A, equal to, I don't know, let's call it 23. Okay? So you need to tell me now number of protons, neutrons, and electrons. Okay? So we can puzzle this out. First of all, we go, okay, sodium. That's easy. I go back to my periodic table. Find sodium, right over here. See that the number that it corresponds to its atomic number is 11. Number of protons, 11. Easy. Not an issue at all. Neutrons. Well, I told you that the mass number is 23, so that means the number of protons, which is 11, plus the number of neutrons, which we don't know, it's got to equal 23. So this number has to be 12. Alright, sodium has a +1 charge, so that means that the number of electrons It has to be one less than that, because otherwise, if they were equal, it would be 0. One too few negative electrons means that this is plus 1 altogether. 11 protons minus 10 electrons, net charge plus 1. That's where that comes from. So that's it. That's as hard as identifying a particular isotope of an atom really is. So you can try this with these 3 examples: protium, deuterium, and tritium. It's the specialized names. Most isotopes don't have specialized names, but for hydrogen, we actually give them their own kind of little names there to go along with the different isotopes. And well, we all know for all 3 of these, we're looking at looking at 1 proton, because this is hydrogen. They're neutral charged, 0 charged, because there's nothing written in the upper right-hand corner here. That means there's 1 electron with each. So the only thing that differs, like we said about isotopes, the only thing that differs is the number of neutrons. So in this case, we must have 0 neutrons. That's possible because we have 1 proton. Protons plus neutrons equals the mass number. And if 1 plus something equals 1, well, that's got to be a 0. Meaning that I have 2 neutrons for deuterium. No. You didn't see that. We have 1 neutron for deuterium, right? That would mean 1 plus something equals the 2. That's the 2 that we see right there. Pretend that didn't happen. Good. Okay, so this 2 right here corresponds to the total of protons plus neutrons, meaning with the 1 proton we must have 1 neutron as well. 1 neutron. So how many neutrons do we have for tritium? Well, 1 plus something equals 3. So 1 plus 2 equals 3. 2 neutrons. Excellent. Final one. I'll stop bugging you. What if you see this? Okay. So we have this particular isotope ion of potassium. Oh, we look at potassium on the periodic table to figure out the number of protons. Scan back. Oh, I went way too far. There it is. We have 19 protons. That's where it is on the periodic table. Good. And duh, we also know that this bottom left-hand corner is the atomic number, which corresponds to the number of protons as well. So if we had this, we didn't even actually need the periodic table, but I'm a chemist. I like the periodic table. So how many neutrons do we have to have? Well, 19 protons plus some number of neutrons equals 40. So this must be 21. Excellent. Positive 1 charge. Okay, so 19 protons. Remember, we can't change the number of protons. Minus the number of electrons. It's going to equal plus 1. So we must have 18 electrons. All right, you're experts in this now. So the atomic mass. The atomic mass is just going to be something that we use to kind of figure out an easier way to measure out a certain amount of atoms. And we can't really measure out individual atoms, so we're going to be measuring groups of atoms out. And those groups are going to have a naturally occurring amount of each of the different kinds of isotopes. if we have two different isotopes of silver, for instance, one that weighs a total of 107 AMUs, and the other that weighs a total of 109 AMUs, the overall average mass of a silver atom is going to be something between that. So if we have a big handful of these things, and we find out through some means that 51.84% of them have a mass of 107, and 48.6 of them have a mass of 109, we can kind of calculate a weighted average mass. Now, no individual silver atom will have that mass, but if you have a large enough group of them, that's the average mass, and you can use that to calculate things about them. So let's calculate this out. How do we do this? Well, it's not exactly 107. If we measure it very, very carefully, one has a mass of, the one that had 107 AMUs was really just a rounding of 106.90509. And this accounts for the slightly different mass of neutrons compared to protons. Same thing here with the 109. You have slightly offset neutron-proton masses, so there's that. So to get the weighted average, we multiply the mass of one of the isotopes times how often we see it. 0.5184 is the fraction that 51.84% represents. So we have 55.42 AMUs worth of silver from that 51%. We multiply the other weight, the weight of the other isotope, by 0.4816. That 0.4816 is the 48.16% that we find as our natural amount of occurring 109 AMU silvers. And this gives us a mass of 52.45. We add the two of those together to get the total average mass, and we get 107.87 AMUs. And this is the weight of one average silver atom. Now keep in mind, again, no silver atom will weigh 107.87. Some will weigh 106 point something, some will weigh 108, but on the average weight of a silver atom, when you have a large group of them, and you're getting the average of that group, is 107.87. Okay, so we can do this again. We can try out this problem. It's more of a concept problem here. I'm sure you've already paused it now and worked it out. We're looking at two isotopes. One, 35, which weighs close to 35 AMUs, and a chlorine 37, with a mass of close to 37 AMUs. The combined mass is a little bit over 35 AMUs. So which of these two, chlorine 35 versus chlorine 37, is going to be the one that we have more of naturally occurring? Now, more of this one. Why? Because in a weighted average, whatever we're closest to must be what has the most weight, meaning the most occurring of the species. Alright, so we credit Mendeleev with the creation of the periodic table, specifically because he was the one that took the elements and decided that we should make groupings of them by showing them written out in increasing atomic mass, which was a measurable parameter through experiment. And when he did this, he noticed as he was listing them out from smallest to largest, sorry, Mendeleev, that every so often you would see similar properties start up again. You'd have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, fluorine, neon. You get back to sodium, and you're like, wait, sodium's kind of like um, lithium was. And you say, yeah, that's fine. And go back to and keep in mind, they didn't know what the periodic table, they didn't have a periodic table the way we do at the time. So when they found that similarity, all this was a big list going from the top to the bottom, smallest to largest. But every so often it's like, oh, this element acts a lot like that one. And then interestingly, the next one acts a lot like the next one after this one. And wait, this third one in that row acts like the third one after here again. So there was this repeating pattern of properties that the elements would have that was discovered by listing them out in this way. So that particular tabulation led to kind of an early version of our periodic table, which lists them according to groupings that have similar properties to them. So part of his proposal on creating a periodic table and ordering these elements is that there were gaps. So you'd have that same kind of repeating pattern that, okay, this one's like that one, and then this next one is like the next one over here in the series, and so on. And then there'd be, wait, there isn't one that looks like this, but over here, there is one that looks like the one if you skip over this. So perhaps this element, which should show a nice repeating pattern with an element that's in between the next set of series later on, maybe we just haven't found that one yet. And that was true. We then went back and were able to fill in the gaps for a lot of these elements and discover them when they hadn't been discovered before. So we didn't know at that point why this periodic behavior was seen, but what we found later on, scientist named Bohr, that we could come up with another model that would start to explain why these periodic property trends were present. So to do this, we have to look at how electrons are situated within the different atoms. And electrons in this way can behave kind of like particles, like individual objects. Right? You can either behave like a particle, like matter, or you can behave like energy and behave like a wave. So in this case, we're describing electrons acting like particles. And the orbits, you could then describe, were kind of like, oh, the electrons are circling around the nucleus in the center, and these electrons are going around in different orbits, meaning different distances away from the center of the nucleus. And these orbits were specified with something called a quantum number, which was just given an abbreviation n. Those distances correspond to a certain amount of energy that the electrons had. So this corresponded with the distance of the orbits, how far away they were from the nucleus, with farther away electrons having more energy than the closer in ones. There seemed to be a very specific amount of space between the orbit levels. And there was also a certain number of electrons you could stick into the orbit that was closest to the nucleus. Then you could fit more into an orbit that was farther away. There seemed to be more room. And then there was a similar number you could put in farther away and farther, and that sort of thing. So the farther out you went, the more you could fit within a couple of patterns and trends. Now, this is an oversimplification, but it works really well to predict how the periodic properties that we see in this repeating list of elements, ordering them from smallest to largest, why those periodic properties exist. And to explain that a bit, what we see is that when an atom has a full outermost orbit, it tends to be very stable, meaning it's not going to react with much, it's going to stay by itself, it's not going to do much chemically in terms of its chemical properties. So what do I mean by full outer orbit? Well, if the innermost orbit, where n equals to 1, were filled up, I could put exactly 2 electrons that close to the nucleus. The second distance from the nucleus, this second little orbital shape, n equals to 2, that could actually hold 8 maximum electrons. The third orbit, also 8 electrons, fourth, etc. as well, 8 electrons, but we're not going to get that far into this. But what this means is if I had an atom and its second orbital has 8 electrons, it's going to be stable, and it's not really going to do much when you react it with other atoms. Now, if you have atoms that are not full at the edge, what they're going to do is they're going to attempt to combine with other things and share or steal or give away electrons so that they will, when they're done, have that full outermost shell, outermost orbit of electrons. And so this two set of things that when they're full in their outer orbits, they're stable. When they're not full, they attempt to become stable by filling up, by sharing, adding, or subtracting electrons, explains a large number of the chemical properties that we see in different atoms of different elements. Alright, so here's our model. Nucleus in the center, electrons circling around the outside, 2 electrons in the first orbital, 8 electrons in the second, 8 more electrons in the third. Alright, so which of these would you expect to be the least reactive, meaning the most stable? Okay, so keep in mind, n equals to 1, 2 electrons, n equals to 2, possible 8 electrons, n equals to 3, 8 more possible electrons. Right, so this is the order that I will put electrons in. So if I'm going to put 1 electron in, it's going to go as close as it can. Second electron fills up that first n equals to 1 distance from the nucleus. The next the next 8 would fill up at the second distance. So now we have the 2 up here plus the 8 down here. If I fill up all of the second level, I've already filled up all of the first level. I've used up 10 electrons. And if I find a home for 8 more by completely filling up that third shell as well, now I have a total of, that was 8 there, so 18 electrons altogether by the time I filled up all 3 of these distances from the nucleus. So if I look at lithium, and it's neutral, lithium from the periodic table has 3 electrons, it's the third element. So that means it has 2 electrons at the first level. And at the second level, it has 1 electron of a possible 8 electrons. Okay, so that accounts for all 3 electrons. Does this have a completely full outermost orbit of electrons? No. Not going to be the most stable then. Okay, so how about oxygen? Okay, oxygen, let's see where it is on the periodic table. There it is. It is the 8th element. So being the 8th element, it will have 8 electrons in the neutral atom. So 8 electrons. Let's start filling up the innermost part first. First level, 2 possible electrons. Still have 6 more. The second level is going to get all 6 of those because it has room for 8. So we can definitely put 6 in there. So that's a total of 8 electrons that we found a home for. 2 in the first distance, 6 at the second distance, 8 altogether in the atom. So what this says is, again, we don't have a full outermost orbital. There's not 8 in that outermost orbital. So this is not the most stable. How about neon? Neon is atomic number 10, meaning it has 10 electrons in the neutral atom. So let's fill up again. 2 of 2 in the first shell, first orbit. 8 more available, so we put them all in the second. That fills up all 8 there. So neon has the last farthest out orbit filled. So this is much more stable than the other two that are in this series. Well, that's how we figure that out. So we're already starting to get an idea from just naming names, a way to work out how individual atoms may or may not be as reactive with things as others. And so now we can look at the periodic table and we can do a couple of things. We can look at where these elements are. And when we do that, we can look at the number of electrons in a particular orbit. And for z equal to 3, what we're looking at is n equals 1, 2 electrons, n equals to 2, 1 electron. So the outermost shell, the outermost orbital, has 1 electron. If we go right below that to sodium, we got z equal to 11. Sodium, this one is lithium. So for n equal to 1, we have our 2 electrons. Still have 9 left. N equals to 2, 8 out of 8 possible. We still have 1 left. Third, we have 1 left. The outermost shell of electrons, outermost orbit, has 1 electron. Guess what we'd see if we went down to potassium? 2 electrons in one, 8 electrons in the second, 8 electrons in the third, 16, 17, 18, 19 electrons to give a space to all together. And again, the outermost orbital has 1 electron. Because the chemistry of an atom tends to deal almost exclusively with what it bumps into, it's the outermost orbits that are going to be the most critical to determining the reactivity and the chemical properties of a particular atom. So we refer to these outermost orbitals as something special, valence electrons. So valence orbitals, or orbits, containing valence electrons. Okay. Notice all of these have the same number of valence electrons. Well, it turns out that all of them in this row, all in this column, have 1 valence electron, and they all have very similar properties in terms of how they react with water, in terms of how they react with other things on the periodic table. They react very similarly because they are all contain the same number of valence electrons. Okay? So we're always going to have 1 valence electron for everything in this first column. We could do a similar workup and find out that we'd have 2 valence electrons in everything in this second column. We completely skip across the more complicated description necessary to understand valence electrons in these middle guys and get over to here and find out that we have 3 valence electrons for everything in this column. You see where this is going, right? 4, 5, 6, and 7 valence electrons, not Z, 7. And finally, in the last row, 8. So these, with actually the exception of this guy who doesn't even have 8 electrons, he has 2. But notice 2 means n equals to 1 has 2 of 2 electrons. So it still has a full valence orbit. All of these in this row have full valence orbits of electrons. So full valence orbits are what make them stable. And so all of the elements in this last final row are extremely stable. And in fact, they're referred to as the noble gases, kind of making a reference to how nobles, kings and queens and that sort of thing don't really associate with anybody else. So they just associate with themselves as well. They don't really react with, chemically, anything else, for the most part. And so given that, in a periodic table, we can go back to our question of which of these are similar, and just look on the periodic table and see what's under in that row, or I'm sorry, in that column, what's under each other. Okay? Calcium, aluminum, not under each other. Lithium and magnesium aren't. Fluorine and argon aren't. Potassium and sodium, if we look at the periodic table, sodium is just right above potassium. So since they're right above each other, they're in the same column, they're both going to have the same number of valence electrons. In this case, 1 valence electron. So they will have similar chemical properties. We have one more type of behavior that we want to look at with electrons. And that's where electrons start acting like waves, like energy instead of particles. So to get a better understanding of how shapes work in molecules and how the connections orient themselves in space, we actually have to replace this Bohr model of the atom with orbits with orbitals instead. And what an orbital represents is kind of a probability that we're going to find an electron somewhere within a certain amount of space, and a certain amount of shape for that space. And now, orbitals are still organized into shells, so first, second, third, fourth, based on distance, but they're also based on the shape that they undertake. S being a spherical shape, P being this kind of lopsided shape, D being kind of a cloverleaf shape, where you can find electrons in these directions, but not in any of these open spaces, and not even in between these. Okay? So we just define these shapes. We can't exactly know where the electron is, but we can be a certain percentage sure that we can find the electron within a certain boundary, and that's how we determine the shape, and then therefore name the shape, and then later on use the shape to predict the overall connectivity and which direction atoms orient themselves in space, which can also lead to properties, chemical and physical properties. That's kind of beyond the scope of the class. We will really get into that later on in a couple of chapters when we start talking about the shapes of molecules, which are atoms connected to each other. But for now, just keep in mind that what we have is this kind of universe where we can't tell 100% where an electron is, and that this other model beyond Bohr's is going to be shown to be very useful in predicting things. Now, Bohr's model about individual particles that circle around an atom like moons around the planet didn't turn out to be true, but the predictive ability of it is very solid. You have to modify this model, the Bohr model of the atom, with this wave nature of electrons and make it a little bit more sophisticated, a little more complicated. But that doesn't mean we can't use that Bohr model and predict a large amount of properties about elements and reactions just by that simpler model. And so, quick statement, multiple choice. Which statement's true for the Bohr model, but not the quantum mechanical, that wave nature of electrons model of atoms? Think about it. Circle it. All right, so we'll move on. Yeah. The Bohr model specifically says that electrons move around in orbits around the nucleus, and that is not the case for the quantum mechanical model. They're more like, I don't know where they are, but they're somewhere within this certain amount of boundary space. And so we can have families of elements because of this. Those are the columns. Some of the columns have names, and we already talked about how they're similar in their properties because of those valence outermost electrons. The first group on the periodic table, and let's look at a periodic table. First group here, group meaning column, is called the alkali metals. They have very similar properties in terms that they're all metallic in appearance. They're kind of silvery and shiny. They tend to burn and catch fire and react strongly when thrown into water. They react with these halogen guys over here in the second to last row in a 1-to-1 ratio. So they have very similar properties all the way down that column. And we can go through and you can look up a whole series of chemical properties for the alkaline earth metals, the chalcogens, the noble gases. All of these things have a certain set of properties that's common to all the members in the group, or as we refer to them as the column, on the periodic table. And all of these groups have names, but these are the more common ones that we kind of want you to know. Alkaline metals, alkaline earth metals, chalcogens, halogens, and noble gases. The center is referred to as the transition metals, all of them. Transition, oh, I'm going to butcher that. Transition metals. Okay. Now, in the general naming of properties, we have kind of a dividing line on the periodic table right over here with boron and silicon and germanium and gallium and all those other guys down here. We have the left side of the periodic table, the left 2/3, and all of these extra elements down here, which are the lanthanides in this row, and the actinides. Did I get that right? I wonder if that's reversed. Actinides. Make sure you double check that. For some reason, I'm just totally blanking on this, and I don't want to record the entire video by dropping out of this and going and checking. Oh, fine. Hold on. Okay. Yeah, I'm back. I went and checked the periodic table just to be sure. Yep, I'm right. Lanthanides, actinides, lanthanides here, actinides here. You know, you can be doing this stuff for 30 years, and every so often things like that you'll just blank on. Like, for instance, the English language, quick side note here, the word both throws me off all the time. I keep thinking that the letter L is going to be in it, and there's no letter L. And then I look at the word half, and I'm like, there shouldn't be an L in there, but there is. And I always think that's somehow connected in some way, that maybe the L from both ended up in half. But in any case, lanthanides, actinides. So the metals are all of these ones in kind of off-white. So everything on the left side plus the lanthanides and the actinides. On the right side of the periodic table in light blue, we have non-metals. These things have a similar set of properties. They tend to gain electrons in reactions. They tend to form compounds in ratios that aren't always easily to predict. They are not metallic in nature. They're more rockish and powdery when we look at them, or liquids, that sort of thing at room temperature. So they're not metallic when we find them. And then we have things that are kind of like somewhat in between. Silicon, kind of like a metal, kind of more like a chalky substance. It has properties of both metals and non-metals, so we call them metalloids. On top of this, when we find some elements, instead of finding them as just individual atoms, some elements actually occur as what we refer to as diatomic molecules. Remember, all a molecule is a combination of atoms in some specific ratio and bonded together. So certain elements, 7 of them to be precise, and it kind of looks like a 7 over here, so we can help remember that. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all form diatomic molecules, meaning that when I find this out in the universe, I'm actually going to find H bonded together with a second hydrogen. Find these attached, a nitrogen attached to another nitrogen. All this little subscript in the bottom right hand corner means is that there's 2 of that individual atom bound together. Oxygen, same thing. Fluorine, chlorine, you get the picture. Okay, so if I find oxygen or talk about oxygen as an element out in the wild, it's going to be 2 oxygens chemically bound together. So to deal with a little bit of the mathematics behind how many, there should be a 3 here, I think I got cut off by my picture. It should be 10 to the 23rd power. To deal with the fact that these atoms are so incredibly small, but we want to weigh up like an actual reasonable amount of them and measure out a reasonable amount. I can't count the amount of atoms that I would have in a handful. I can't count billions of billions of billions. It's just not possible. It's not practical. So instead, we define a quantity called the mole. And a mole is 6.022 approximately times 10 to the 23rd power as a multiplier. Well, what do I mean by that? Well, if I have 12 things, what do we call it? We call it a dozen. Okay? If we have a mole of things, we have 6.022 times 10 to the 23rd of them. That's a mole. What I find is really entertaining is we abbreviate mole as MOL. Right? Because that E would have just been too hard to add on to the end of it. That would take way too long. Right? So what's in a mole? Well, about 22 copper pennies have about a mole of copper atoms. We have 6 helium balloons. Helium is a lot less dense. It's more spread out. Helium, 1 mole of helium atoms. We need about 6 good-sized helium balloons for that. But this is, a mole is a reasonable amount of material to be able to pick up. Now keep in mind, moles and moles, that's the same size, meaning that the amount of atoms in this handful of pennies is the amount of atoms in these 6 helium balloons. It means that these balloons, the gas is much less dense than the solid copper is in the copper coin. So where did we get this number? Well, we got this number so that we can take the mass in AMUs and we can have a certain number of these individual bits of the atom in a big pile of those atoms, and we can take that 6.022 times 10 to the 23rd and have a certain number of AMUs and a certain number of individual objects, and when you work that all out, then you can get 2 ratios that are very similar. You can have the ratio of AMUs of matter per individual atom, and that will be exactly equal. That ratio will be exactly equal to the number of grams that I have in 1 mole of atoms. Okay, so that number of items that we have that gives us this equality, that this ratio, not that AMUs equal grams, not that atoms equal moles of atoms, but that the ratio is the same. That number that allows us to do that, the 6.022 times 10 to the 23rd power, is referred to Avogadro's number, determined by a scientist by the same name. Now we can use these sort of relationships as conversion factors, just like 12 inches to a foot and other things of that nature. So let's try that. It's 3.1 grams of copper in an average US penny before 1982. So how many moles of copper did that represent? Okay. Well, we know from our periodic table, we can look at the periodic table and we can see an averaged amount. Right under the copper, for instance, if you look at your periodic table, or right over it, depends on the periodic table you're looking at, you'll have this number 12 0.01 or something close to it. You can have different numbers of measured precision digits on this. But under the carbon or above it, you'll see this 12.001. That's the measured, including the weighted average of isotopes present for that particular type of element for the average AMUs per one carbon atom. And as we just talked about before, that also then corresponds to the number of grams per mole of carbon atoms. Carbon. So if I have 3.11 grams of copper, the symbol for copper is Cu. We can go to a periodic table and look up this little number here for copper and see how many grams there are per mole of copper. Use that as a ratio, just like any other conversion we've done, and end up with, at the end, moles of copper. Okay, so go to your periodic table, take a look at this. Okay, so if you looked up the periodic table, you can see that there are 63.55 grams of copper for every 1 mole of copper. That's the number that's written on the periodic table for copper. So if we want to use this, we just have to flip this the direction that we need in order to have the grams of copper cancel out with the grams of copper here, and the moles of copper be where we need it to be to give us an answer in moles of copper. So moles of copper must have to go on top, and grams of copper must have to go on the bottom. So 1 mole, 63.55 grams. Pull out a calculator and see what we get here. And what we get is 0.0489 moles of copper. And that's the answer to our question. One more here. 85 kilogram human contains about 4.25 grams of magnesium. So how many atoms are in 4.25 grams of magnesium? Same idea here. We're going to take the 4.25 grams of magnesium, multiply it by a ratio that gets rid of grams of magnesium, and puts moles of magnesium on the top. But then we're going to also multiply this by that there are 6.022 times 10 to the 23rd power of magnesium atoms. And this is where you get to try out that key on your calculator. It says EE. Right? This would be 6.022 EE23. And there's that many atoms of magnesium for every 1 mole of magnesium atoms. And let's see what we get here. Well, first of all, what we have to do is we're going to have to figure out what the number of grams of magnesium there are in 1 mole. So to do that, we go to our periodic table. So we go to the periodic table and I find 24.31 grams magnesium. Okay, so now we just need to plug through and calculate this out. 4.25 divided by 24.31 24.31 gives us about 0.174. We're going to multiply this by 6.022 e to the 23rd, and we get a number that is 1.05 times 10 to the 23rd power. Okay? So this is how that works. That is the units of magnesium atoms, moles, grams, those all cancel out. We're left with just magnesium atoms. So that's what we have here. We have 1.05 times 10 to the 23rd individual magnesium atoms. So finally, to summarize this, we've talked about atomic number and mass and isotopes. We've talked about molar mass, which is that idea of the number of grams per mole of a substance. We've talked about the two models for atoms and how they relate to orbitals. And all of this relates to all sorts of ideas in your book, specifically how the main one being all of these chemical changes that we see in the world around us are just due to changes in the connections of atoms and molecules and atoms in molecules. The book also likes to talk about models and interpreting nature and how pollution is just atoms where they're not supposed to be. But that we're not going to cover as deeply. You can cover that, read through that in the book. It's interesting stuff.